elementary equivalence, which is a fairly basic notion in model theory and of importance. So what we are basically going to do is to look at issues on expressiveness. So far we have talked about semantics of first order logic, models for formulas, and then we went into deductions and reasoning and some questions that we raised which were more algorithmic in nature. And then there is this question of the third dimension, which is also apart from semantic consequence and deduction, question of expressiveness of logical languages. Expressiveness, we already talked about it a little bit earlier. So in general, when you have a structure, if you fix a language L and look at a first order structure, then a sentence is either true or false in it, right? So we can talk about the theory of the structure as sentence is true, or we can talk about models of phi to be structures yeah. So we already have this notion, and we say that a class of structures say K kappa is definable if there exists a sentence phi yeah. So this is the notion of definability, and then there is also this notion of definability in a structure. If I have a structure A, yeah, with some a domain and an interpretation, then we say that a relation R subset of A to the n is definable in whatever is the logical language that you are talking about if there exists a formula alpha with, let's say, free variables x1 through xn. This is just notation for saying these are the free variables. Free variables are among x1 to xn, such that now if I consider A with some tuples a1 through an satisfies alpha, if and only if yeah, if I take all the tuples that satisfy alpha, this notation is to say the free variable x1 is getting the value a1, x2 gets a2, and so on, xn gets an. Under this assignment, this model satisfies alpha, right? If and only if it's in the relation. So basically, if I look at the set of tuples defined that make the formula true, that's exactly the relation R. So we talk about something as definable. So there is this, so this both this idea of a structure being definable in a language, and then a relation being in a structure being definable in a language. These are things that we have talked about. Now, and as I pointed out, if a particular structure is definable, right, all you have to do is to write a sentence for it, right? If, for instance, I want to say that in the language of groups, the class of abelian groups is definable, I just write a sentence, right? The sentence is quite trivial. For all x, for all y, x times y equals y times x, where times is a group action. That defines, that sentence defines the class of abelian groups in this. Similarly, I have, for instance, I want to say ordering is definable in arithmetic where you have addition, right? I just have to write x less than y. For x less than y, I write the formula. There exists z greater than 0. Oh, well, I don't have ordering. Yeah. Sorry.
Not equal to 0.
Yeah. Yeah. Z not equal to 0 and x plus z equals y. Yeah. And this is a binary relation, right? It's a formula with two free variables. And if you plug in all the values, right, in the reals that make this true, that defines the order relation. So in that sense, order relation is definable. Now, as I said, there are lots of examples like this, and yeah, any, yeah, sorry.
Sir, like in over here, definable in L. So we have a fixed language.
No, this is definable in a structure. This is, I'm sorry, this is important. This is definable, L definable in the structure. Yeah. This is relative to a structure. So when I say the ordering relation is definable in the structure R plus 0. Yeah. Anything else? Is this clear? So yeah, so this is where the interesting thing comes. If it's definable, you write a sentence, right? If a structure, if a relation is definable in a structure, write a formula for it. But what if it's not definable? How would you prove that it's not definable? Right?
Yeah, sorry to interrupt, Mr.
Yeah.
Purandar.
Yeah.
Here you want Z to be positive, so.
Oh yeah, that's true. That's
so
true.
you want natural numbers or something? Or
No. So what? Can you tell me what I should do? Somebody. Yeah. I want Z to be positive, right? Let me take the language of fields for now. In fact, it's definable with addition, but let me. Yeah. That's the. There exists Z. Yeah. I want to say Z is positive. Yeah.
There exists a Z such that x plus z square equal to y.
Exactly. That's what I was going to. So that's why I went to the. Yeah. When I go to the language of fields, it's straightforward. You have to do it. You should do it with in the language of groups as well. But think about how you will do it. Okay. Good. Nice. So there's a lot of programming to be done to define particular relations in terms of others, right? That's really a programming exercise, programming in logical languages. Like Siddharth just came up with this, right? I mean, this is just a very simple way of making sure that it's positive. Yeah. Okay. But thanks, Purandar, and that was important. Yeah. The point is that, anyway, today's topic is not about definability at all. It's about indefinability. The whole thing is what kind of tools and techniques, I need some tools and techniques if I want to show that something is not definable, right? To show that something is definable, you just have to write a sentence. But something is not definable, you have to find some closure condition, some way of saying, oh, this is there, but that is not there, etc. Right? This is the usual game that we play, right? So, and for that is the main idea that how do we talk about structures that satisfy same formulas, and that is the idea of elementary equivalence. We'll get to it. So, and that's what this is going to be about. But before that, before we get to elementary equivalence, something which we probably should have done long ago, which is sanity check, right? Once you have a semantics, right? If I have a semantics, a model satisfy alpha, right? Or your structure satisfies a sentence, right? Notice that immediately the semantics generates an equivalence relation on all structures, right? Two structures are equivalent if and only if they satisfy the same sentences. Two models, right? A is equivalent to B if and only if for all phi, and this is called elementary equivalence. Basically, it says that your language cannot distinguish between these structures, right? That's what it says, right? Take all sentences, they both satisfy the same sentences, right? That's exactly what it's saying. Is it clear? This is a natural equivalence relation induced by the semantics. Now, of course, I have to define it for formulas. So, M1 is equivalent to M2 if and only if for every formula alpha, alpha is true in M1 if and only if alpha is true in M2. Yeah. So, in general, we'd be interested in equivalence on models, and this is the notion of elementary equivalence, either structures. This is what we are most interested in, but of course, in the process, we have to look at this. Now, whenever you consider something like that, like I said, there is a sanity check to be made. What is that? Well, this is some fancy equivalence relation, but there is one equivalence that must be respected by the semantics, and that is isomorphism, right? If two structures are isomorphic, they better satisfy the same sentences. Otherwise, something is wrong with the way you have done your semantics, because the whole notion of isomorphism is that there is no way to distinguish the two, right? So there should not be any way to distinguish them using your semantics either. So, but then how do you define isomorphism? For that you have to define homomorphism. How do you define homomorphism? Let's just go through the exercise. As I said, this is sanity check. So, as I said, let's write to say if they are isomorphic, then we want yeah. Okay. So what is the idea of homomorphism? So let me write so fix a language L. Let A, B be L structures. So A is with domain A, interpretation A, and B has domain B with the interpretation function, interpretation over it for whatever constant symbols, function symbols, predicate symbols you have in the language. These are the two structures that are given. A map H from A to B is a homomorphism of structures. Well, what's a homomorphism? It preserves structures, right? Homomorphism is a map that preserves structure. Now, what is the structure that you want to preserve here? The interpretation of the interpretation should be preserved, right? So, therefore, first condition, L has some constant symbols. So, L is fixed for all C. The H of interpretation of C in this structure is, yeah. If I take the interpretation of C in A and apply the map H, I should get the interpretation of the symbol C. This is what it means to say I preserve the interpretation of constant symbols, the meaning of constant symbols. Yeah?
So what's written I cannot, for all?
For all constant symbols.
Sir, shouldn't it be idea of H of C?
H of, not C. C is a constant symbol. Take the interpretation of
interpretation over B.
The interpretation of C in A is what that's an element of A, right? Apply H, you get an element of B. That domain element B should be the interpretation of the constant symbol C by the structure B. IB of C, right? Is it clear? IA gives me, for every constant symbol, it gives me an element in A. IB, for every constant symbol, it will give me an element in B, right? They should cohere, right? Anything else? Okay. Similarly, now, for every KRE function symbol in F. What do you want? H of F, I have to write the interpretation function, right, of A1 through AK equals, right. Now, I take a K tuple in the domain A, apply whatever is the interpretation you are giving me here, I get some element of A and I apply H to that, that should be the same as the B interpretation of F applied to H of A1, H of, right?
Sir, yes. So
AK,
what I
sorry.
was asking in the first one.
Yeah.
ID of H of C, right side of the equation.
No, of course not. Look at this. IA of C is some element A belonging to A, right? I apply H to it. H of A is some element B. Now, IB of C is some B prime belonging to B, right? This belongs to B. What the statement says is that B equals B prime. Is this clear? In the structure A, the constant C is interpreted as an element A in the domain of A, right? Now, when I apply H is a map from the domain A to domain B. It will give me some element of this, yeah? Let's just call it H of A. H of A belongs to B, yeah? And this is the interpretation for C, the constant symbol C is according to the second structure, some element B. Now, what this says is that H of A equals B is a condition there.
Okay, sir. Okay.
Yeah? Yeah, it's just some bureaucracy. And we are used to doing this, right? We want to say that H of, for instance, when the function is addition, you will want to say that H of A1 plus A2 is the same as H of A1 plus H of A2, right? Except that this is a plus 1 here and there is a plus 2 here, right? Typically, this is how you would write A1 plus A2 equals H of A1 plus B H of A2, right? Where this is the addition operation in this structure and this is the addition operation in this structure, right? And in algebra, you do a lot of such homomorphisms, right? For instance, I could map addition on this structure to multiplication on this structure, right? So that you will say that, when I add two elements, it maps to the product there, and so on. And this is exactly what we.
That's where I got confused.
Yeah.
Because usually in homomorphism, H appears on both sides.
Where does it appear on both sides? Here. Are you talking about this one? No, this is okay. Yeah, look at this again. H of A1, this is an element of B. This is an element of B. Yeah. So this is a tuple of elements in B. Your interpretation function now maps K tuples of elements of B to an element of B, right? Which is what you want. So this is, so you take an element of A to an element of B. Is it okay?
I was thinking, sir, why is it not like this that in the left and right hand side, I'll say, the left hand side should, why is it not that iota A, in the iota A of A1, comma, iota A
No, it's not.
P1.
No, it's not.
P1 is a third.
Yeah. So no. This is not with terms. This is with structures, right? Here is the language which gives you some constant symbols, function symbols, predicate symbols, right? Now we are only saying that interpretations are preserved. What is interpretation preserved? You have to preserve the interpretation for constant symbols, preserve the interpretation for function symbols. For predicate symbols, I have to write one more, right? Now, for function symbols, what do I need to do? I take a function symbol, k-array function symbol. The first interpretation gives me a function, right? That function, which is what I have written here, takes k tuples of elements of A, right? And gives me an element of A, the domain A. I apply H to that, I get an element of B, right? What is that element? That element is equal to, this is what it says. Now if I take the interpretation, That's exactly like this, right? I take the plus function here on the right hand side and I apply to h of a1 the image elements that I have got here.
Yes.
Right?
Yes, I get it now.
Yeah. So this is exactly this, right? I mean, typically, for instance, supposing I map the addition, this is what you do usually. You take the product and map it to a sum, right? Homomorphisms, right? Very often are things of this kind, right? That's all that we are talking about, except that we are saying it in general. So, in fact, the point is, like I said, when I introduce theories, right? Now you realize that whatever you've been calling group theory and category theory and K theory and whatever are theories in the sense that we are talking about, right? Theories of these structures, right? With respect to a particular language that you have. Similarly, the point is to recognize that whatever you've been calling homomorphisms, well, you talk about group homomorphism, field homomorphism, whatever else your favorite structure homomorphism, graph homomorphism. Now, this is all the same thing, right? Any homomorphism of structures, once you understand, that particular thing is what you have been talking about, right? So, there should not be any surprises in this. That's important because this is exactly what we have. Otherwise, we'll have a problem trying to prove anything also. So, now if you take an Emery predicate symbol, right? Now, what is going to happen? Your predicate symbols again map m tuples to some 0 1, right? And you want to make sure that that happens there as well, right? So, what you want here is that no, one moment, yeah, a1 through am belongs to, this is a Emery relation here, right? So, this m tuple belongs to the interpretation on the left hand side if and only if h of a1, h of am belongs to interpretation of P the right hand side, and this is again exactly what you would expect, right? Preserves relations means that whenever you're talking about an Emery relation, an m tuple is there, belongs to the interpretation here if and only if I take pointwise image, form the m tuple, and that gives me a relation on the right hand side. Yeah. So this is the idea of a homomorphism, and we are used to normal, for instance, this is a standard homomorphism, right? If I take positive integers with the ordering on positive integers, let's say this is a and b, natural numbers to natural numbers, yeah, h of x equals x minus 1, yeah, I should write numbers, no? So that's a homomorphism, right? It also illustrates a particular case of homomorphism when yeah, okay, so let me also introduce some more terminology that we use. Let's get rid of all these which we want to get. When H is injective, we say it is we call it it's called a homomorphic embedding of A into B. This is standard terminology, so I am just when H is also surjective, we call it an isomorphism. So, an isomorphism of structures is simply a homomorphism which is 1 1 on 2, right? Exactly what you would expect. So, and in the special case where A happens to be a subset of B, then it's easy to see that IDA is a homomorphism right? The identity map. If you are talking about two structures where A is actually contained in B, that's an isomorphic embedding, right? We are the identity, and in that case you call a substructure of B, and this is the probably A is called a substructure of B and B is called an extension of A. So in this,
all embed.
sorry,
So, but aren't all embeddings isomorphic? Like
no,
indexes.
no. Identity I said is a homomorphism from A to B. Yeah, A is contained in B, right?
So, but what did you mean by isomorphic embedding?
No, I said homomorphic embedding.
Okay, okay, sorry, sir, sorry.
I'm sorry if I said isomorphic as wrong. I meant a homomorphic embedding. Yeah. No, no. Either you have an isomorphism or not, right? Then there is no need to embed anything. Yeah. So I am talking about a specific case. In this particular case, where A is a subset of B, right? You can talk about A being a substructure of B, and this is exactly the sense in which you talk about A being a subgroup of B, or A being a subalgebra of B, or A being a subgraph of B, or whatever, right? So the notion of substructure, for instance, in the case of graphs, right? The natural notion, that is the induced subgraph, right? You will see that that's exactly what it means, because you want all the things to be preserved, right? So so this is the notion of substructure, and A is a substructure of B is the same as saying B is an extension of A, right? And okay, that's an important notion. What else is needed for so for instance here it's clear that, so the notation used in this case is, at least this is what I use. I'm not going to do too much of all this stuff, but if we did some model theory, probably we'll do more of this. Yeah, this particular case. Yeah, and yeah. So now let us do the sanity check, right? We want to show that if two structures are isomorphic, they satisfy the same sentences, right? Now I've defined a homomorphism of structures. We can also talk about a homomorphism of models, right? If I have M1 A IA pi A and M2 B pi B, it's a homomorphism of models if, obviously what you would expect, H of pi A of x equals pi B of x for all x belonging to, yeah, variables. Obviously that's what you would want, right? So that's a homomorphism of models, so that the variable assignments are also preserved by the homomorphism. So this is homomorphism of models. Okay, so I think the definitions are straightforward enough, so I can take it off. It's more a matter of internalizing what the intention is. And here is our proposition, which is our sanity check, except that I'm going to write it in 2-3 steps, and that's useful. That's why proposition. So this is all with respect to a particular L. So let M1 A IA pi A and L models and H Yeah, it's a model homomorphism. Then I'm only talking about homomorphism here, not isomorphism. Right? Then 1 for all quantifier free formulas without equality alpha, M1 satisfies alpha. So the point is that our homomorphism preserves truth of quantifier free formulas without equality. And this proof is obvious. Why? Well, if it's a quantifier free formula, what is the base case? Well, it can't be equality, only predicate symbol, right? So first thing is that if H is a homomorphism, you know that for all terms H of pi hat A of t is pi hat of B of t. And this is something that we can prove. So this is an observation. I think this is what earlier one of you mentioned, right? So base case, you take this is proved by induction on structure of terms. Base case where it's a constant, then we have already said this is an interpretation A of C gives you the interpretation in B of C. For variable, well, we just said it's a homomorphism of models, so therefore pi A of x, H of pi A of x is pi B of x, so it's okay. Then inductively evaluate the terms and take for a function symbol, you will see that it works neatly. So this is true. So once you have this, right, M1 satisfies P T1 through Tm if and only if pi hat of T1 to pi hat of Tm, this belongs to interpretation in A of P. By homomorphism, if and only if H of pi hat of T1, this is all A, pi H of pi A hat of Tm belongs to this, and by observation there, if and only if, so this is pi A, yeah. There is a kind of comfort in doing such boring bureaucratic proofs because there's nothing much, right? Okay, because it must go through. I mean, what else can it do, right?
Sir, but equality would also be taken care of.
No, of course not. You will see. Just a moment. Just a moment. Huh? Let's just make sure that this goes through, right? So that is the base case. Now you are only left with it's quantifier free. So your formula alpha can be of the form not beta or some boolean, right? Beta 1 or beta 2, right? Let's say that's enough. Okay, M1 satisfies not beta if and only if M1 doesn't satisfy beta, if and only if by induction hypothesis M2 doesn't satisfy. Boolean cases must go through, right? So this is clear. What about equality? Let's try equality. M1 satisfies T1 equals T2 implies pi A hat of T1 equals pi A hat of T2, which implies H of pi A hat of T1 equals H of pi A hat of T2, which implies pi B hat of T1 which implies M2 satisfies T1 equals T2. Very good. So, left hand side implies right hand side is trivial. What about right hand side implies? So, this, well, this implies pi b hat of T1 equals pi b hat of T2, but from this, how do I go to this? Yeah, is not clear anymore, and that is why you have to have this extra assumption. So, now I can write, thanks to Swapnil for pointing out exactly what is needed. 2. If H is also surjective, no,
Sir,
injective,
sir,
one moment, H is also injective, then for all quantifier free formulas alpha, yeah, yes,
shouldn't it come in the next,
huh?
next implication, the upper?
Yeah,
Yeah,
yeah.
the question mark should be in the upper one.
Oh, okay, yeah, yeah, that's true,
It's
that's true, that's
H2
true, that's true,
means P, right?
absolutely, absolutely, you are absolutely right. Yeah, yeah. If H is injective, of course, if H of x equals H of y, then x equals y, right? And that's exactly what you. So, if H is injective in addition, the equality case also goes through, and it's a fairly routine exercise for Swapnil, especially now, since you asked this, to come up with a homomorphism of structures which is not injective and show that equality gets violated, right? I mean, so you should do some exercise, and that makes sense because many things when they map into one, so you have things that are distinguished in the structure A getting collapsed into the structure B, right? So that's why, yeah. So you don't have the if and only if. Is it clear? Okay. So now, if H is also surjective, then for all alpha, now you have an isomorphism. It's a homomorphism that's injective and surjective, and so now when we do the induction, atomic formulas are taken care of, equality is taken care of, negation, disjunction is all taken care of, only quantifier case is left. And it's exactly for quantifiers that you need surjectivity. Let's do the proof. So suppose M1 satisfies there exists X alpha, then for some element A belonging to A, M1 with X getting mapped to A satisfies alpha. That's why you need a homomorphism of models, right? Homomorphism of structures will not do because you want to go over to that particular model, right? Implies, yeah, yeah, M2 with X mapped to H of A satisfies alpha by induction hypothesis, right? Remember, induction hypothesis really says for all models M1 and M2, if you have a homomorphism, right? If you have a homomorphism, then this model with whatever assignment you have got satisfies alpha if and only if in the right hand side the model with the homomorphic image satisfies alpha. That's exactly the homomorphism of models. Now you gave H and I have extended now H to a H prime, right, where it's mapping the element A to appropriately to H of A. The variable, the pi 1 and pi 2 that I am looking at is mapped appropriately, and this implies M2 satisfies there exists X alpha. Now it's clear, so it's clear again that going from M1 to M2 you don't need any assumption, but M2 to M1 will require surjectivity. This should also be obvious. If M2 satisfies, there exists X alpha, right? Let's start with this. If M2 satisfies, there exists X alpha, then there is some B such that this satisfies alpha. Now, by surjectivity, H being surjective, H is surjective, therefore, for some A belonging to A, M2 with X mapped to H of A satisfies alpha, right? That is the meaning of surjectivity. That means, therefore, by induction hypothesis, for some A belonging to A, M1 with X mapped to A satisfies alpha, which implies okay. So it's a pretty, as I said, this is just sanity check, but I think it's important to understand exactly which part of the definition you need for which part of the proof. That's why I thought, I mean, in general, this is how you write it in proof. If two structures are isomorphic, they satisfy the same sentences. That's what you are looking for. But to prove that, in the induction step, you will have free variables and so on. So you have to consider if two models are isomorphic, then you show that they satisfy the same formulas, and you start doing it. So you use surjectivity in one place, injectivity in one place, and the preservation of structure all over the place. Everywhere you use it, right? So I hope this is clear. Any questions related to this? So this should be absolutely clear that if if two structures are isomorphic, then of course they satisfy the same sentences. So this is now. So we have two notions now, and that's what is interesting in this whole business. So this stands for A and B are isomorphic. This is tied to L. Two structures are isomorphic, that is not, well, the way we have defined it, it's an L homomorphism, so it's always with respect to L, right? And so it's clear that that's what we have just said. If isomorphic structures satisfy the same sentences, what about does elementary equivalence give you isomorphism? What does that mean? If it were true, let's just see what would be the implication. If it is true, that means every structure can be defined up to isomorphism. That's what it means, right? Because if conversely, if this were true, that means if two structures are non-isomorphic, then there is at least one sentence distinguishing them, right? Yeah. So that there exist non-isomorphic structures that can be distinguished, yeah, for the logic. And so that's a way of saying that I can describe structures up to isomorphism in the logic, right? And so this is part of the project that I began with, right? I said, well, the whole point about talking about such structures in logic is that you want to define structures by their properties. You want to define elements by their properties, right? This was part of the whole agenda that we began with, right? Something like 0. When you take the number line, you start with 0, 1, 2, 3, this is how you start in primary school, and then you realize that, okay, 2 stands for the equivalence class of objects with 2 elements, right? Okay, 0, if we are talking about in the number line, represents the minimal element, right? Call it whatever you like. The fact that it's the property that I am interested in is that it's a minimal element, right? So this is what we want to do. So we want to write properties and describe these, and so can one define a structure up to isomorphism? For instance, this is our favorite yeah, just the number line, right? And I don't need structure because successor, because I can always define the successor function in first order logic from less than, yeah. And so this is a number line. Can one define this structure up to isomorphism, right? Can I write a set of sentences that describes this up to isomorphism? This is the kind of question that we are interested in. First, let's see that firstly this is false, and it's easy. Yeah, this is false. Elementary equivalence does not imply isomorphism, because example that I took already shows this. If I take less than p, okay, this is not example for that, but I said I have a homomorphism yeah, positive integers to natural numbers, right? What is that? H of n equals n minus 1. This is a homomorphism, right? And a homomorphism preserves what? Therefore, I know that these two structures satisfy the same atomic formulas, right? Without equality. That's about all you can say, because there are formulas that distinguish the two, right? For instance, in this case, if I take with its ordering and x evaluated to 1, that satisfies for all y, x not equal to y implies x less than y. Whereas if I take does not satisfy. Yeah, because 1 is the minimal element here, but it's not the minimal element in this, right? So there is a distinguishing sentence. Yeah, and okay.
Sir,
Yeah.
shouldn't we be taking h of 1 instead of just 1?
Oh yeah, I should take h of 1, but no. I'm saying that yeah, that's true. What you are saying is true, but I'm just saying that with this assignment, right, with this particular model, these two sentences are not satisfied. I agree. I agree that with h of 1 it is true. Yeah. Yeah, I mean, yeah. Now I want to look at structures that are elementarily equivalent but not isomorphic. That's what it means to
Yes,
say.
sir. Yeah, but over here they are isomorphic, so they are elementary equivalent. So we will not be able to find a sentence which is true in one but not in the other.
Sorry.
So over P and N, they are isomorphic. No, they are no, they are not isomorphic.
They are not isomorphic. So yeah. Yeah. So, okay. Consider these two structures, and that's what we will take. We will show that, but of course they are not.
Sir, but they are isomorph, sir. But I don't know, sir. But this H, sir.
Yeah.
This is an isom. This is a bijection. This is a bijection. So this is an isomorphism.
Okay.
So they are They are elementary equivalent.
Okay.
E and A.
But then they satisfy the same sentences, right?
Yeah.
That's why I'm talking about their truth at a particular with a particular element, right? And like what he's pointing out is that if I were to compare them as models, right, and that is what Siddharth was talking about. If I talk about x at 1, here I should talk about x mapped to h of 1, which is 0, right? So that's what you were pointing out, right? I agree.
Yeah. So sir, we have to find a model where in like where they are true. They are true. Like if A of in under interpretation A it is true, then if and only if under interpretation of B it is true, then we have to find a sentence which is we have to show that they are not isomorphic.
Yeah.
That is what we have to do.
Oh, that's okay. No, I was making a different point. I mean, I was talking about when you evaluate formulas at a particular elements, you have to be careful. That's all I was talking about, right? Yeah. When you are going across, the same element may mean something completely different, right? Even though it's a substructure, right? It's a substructure of the other. The element has a different meaning, right? When you go into this, that's all that.
Right.
Yeah. Oh, sorry, it was probably a distraction. I mean, the point I was trying to make was that elementary equivalence does not imply isomorphism, right? That's what I want to get to. And the classic example is this: rationals with their ordering, right? Certainly not isomorphic to reals with the ordered set of reals, but they are elementarily equivalent. But how do you prove that they are elementarily equivalent? That takes some work. But before that, it's also important. So that's a more complicated argument. Before that, let me take something simple, which is, okay. So we talked about this, right? When we say that, we can talk about automorphisms, right? When you have an isomorphism from A to itself, of course, that's what you call an automorphism. And there's a fairly simple, very straightforward proposition, which is that automorphisms preserve definable relations. This is very important. If R is definable, that means what? You have a formula, right? You have a formula such that the set of all n tuples which satisfy the formula is exactly R, right? So if R, there is a formula alpha in the language L such that A with A1 to An satisfy alpha if and only if belongs to R, right? Now you have the automorphism H. That means what? That means A with H of A1, H of An satisfies alpha, right? If and only if H of A1 through H of An belongs to R. This is the same as saying automorphisms preserve definable relations. Automorphisms are preserved under, I don't know which is the correct way to say it. Yeah, definable relations preserve automorphisms. Sorry. What I'm saying is that if R is a definable relation, A1 through An belong. If R is a definable relation, then A1 through AN belongs to R if and only if H of A1 through H of AN belongs to R. Yeah. Probably I should write definable relations preserve automorphism, not the other way. But okay, this is the correct, and that is obvious. This can be used to show that certain relations are not definable in your language. Let's see. We'll get to that. This is a useful thing to do. For instance, if I take the set of reals, right, consider h of x equals x cube or x squared, whatever, right. Now this is an automorphism. In fact, it's an automorphism onto natural numbers, right? Because cube root of every natural number is sitting in the reals, right? So H maps elements outside N onto N, possibly outside N, right? In general, the domain of H, if I take the inverse image of N under this map H, you're going to get things that are. So this tells me, this automatically tells me that the set of natural numbers is not definable in the. When is a set definable? Well, there is a formula with one free variable, right? A particular subset of the reals is definable in the structure, in the ordered set of reals, if there is a formula with one free variable such that the set of all elements that make it true is exactly what you began with. So this says that the set of natural numbers is not definable in, and this was one of the early and important things in this area, where because Tarski proved that the set of real arithmetic is definable, real arithmetic is decidable, and so if natural numbers were definable, then you would get a decision procedure for arithmetic as well, which you can't, as Gödel showed. So all these things were there. So which are the definable subsets of reals? That's one of the holy grail thing. Okay, so if your language has only well, with function symbols it gets really hairy, so let me not go there. So I'm just saying that automorphisms can be used to show some things are not definable. That is a classic example that you will find in texts. For instance, if I have vector spaces, if I have the plane and addition of vectors and times R scalar multiplication. If this is the structure that you take, right, and then you can show that, let's say, everything that maps, so every vector x to 2 times doubling is an automorphism. Okay, automorphism on vector spaces are linear transformations, and this is just a linear transformation. So this tells me that the set of elements whose length is 1, right? Unit vector is not definable, and this is something that you find in text, right? Unit vector is not definable, length is not definable using addition and scalar multiplication. This is one of the things that you do in linear algebra, and this is one of the things to say that this is not definable, because Here is an automorphism that does not preserve it. Right? So automorphisms preserve definable relations is one standard trick to show that certain structures are not definable. Right? So in general, how do you show that a particular relation is not definable? Come up with an automorphism such that this particular property is not preserved. Yeah, this is the recipe. So now, and to show that some property is not, some structure is not definable, how will you show that? Well, to show that if it were definable, there would be a sentence defining it, and then you take two structures, one which satisfies the property and one which does not satisfy the property, and show that they are elementarily equivalent, and then you are done. So that's why we are doing all this business. Yeah. So it gives you a recipe for showing structures not being definable. Automorphism is the way to go for showing relations not being definable in a structure. And these are simple examples. There are very nice exercises in model theory books. They're full of fancy exercises for many of these. Maybe I'll give you one or two with arithmetic. For instance, to show that if I have, with addition, multiplication is not definable, right? That's a natural question too. That is, if I take order with addition given to me, and I want to show that the relation is not definable. This is already a non-trivial exercise, but in general, this is the sort of thing that you are after. Okay. Okay, let me get to the statement that so clearly the set of rationals, this is not isomorphic to the real, so that's not a problem, right? So you just have to show that these two are elementarily equivalent, right? How do you show that they are elementarily equivalent? Well, that's difficult. So one way is to show that, okay, so this is one of the nice really beautiful theorems. Yeah, take any two structures. So consider the theory. This theory is called in model theory texts, it has this, you will find this abbreviation. So this stands for dense linear order without first and last elements. Okay, take any two linear orders which are dense and has no minimal element, maximal element, right? And so if x1 are two linear orders without first and last element, dense linear orders without, then we can show that these two structures are elementarily equivalent. So this, what axioms it will have? It will have linearity axioms, right? What are they? For all x, for all y, either x less than y or y less than x or x equals y, it's total. For all x, x is not less than x, not of x less than x, not reflexive and transitive, right? For all x, for all y, for all z, x less than y and y less than z implies x less than z. So this is the linearity axiom. And then dense. For all x, for all y, x less than y implies there is a z such that x less than z and z less than y. No minimal element. For all x, there exists y such that y is less than x. No maximal element. For all x, for all x, there exists y such that x is less than y. That's it. So that will describe the, take the conjunction of all these formulas, that is your theory, look at all the models of that, right? Now what I am claiming is that if I take any two models in this class, right, that they satisfy all these axioms, then they are elementarily equivalent in the language of order. How do you prove that? Oh no, I want to say that they are isomorphic. I'm sorry. I'm going to show that take any two, they are isomorphic. And if they are isomorphic, of course, they will satisfy the same sentences, right? How do you prove that? So, first claim is that they are isomorphic. Second is that if they are isomorphic, yeah. Second is Cantor's theorem. Any Dlohful is isomorphic to. Cantor's theorem says that if you give me any model, any dense linear order without first and last elements, it's actually isomorphic to the rationals. Okay, and so it's really a very nice statement that. So now if I take this particular theory, right, let me call this theory gamma, right. Now if I am looking at con of gamma, right, yeah, and this is actually a single sentence, right, because this is finite, so I don't even need a set, right, I can talk about, yeah. And clearly R satisfies these sentences, right. It's a dense linear order without first and last elements, yeah. And so I have to use countable model, so somehow maybe I should get to that. A lot of things to do, yeah. Okay, so let's see how you will do. How do you show that these two are? Okay, so there is some little more work to be done. I have one more thing to prove before we can actually get to this. That I have to show that this is a complete theory. Yeah. Yeah.
Sir, I don't understand this. That if any DLO substitution is isomorphic to Q, then then these two will also be isomorphic. I started that up.
Of course, I'm sorry. Any countable dense linear order without first and last elements is isomorphic to the order of rationals. I'm sorry, that's a very important, and yeah. This is Cantor's theorem, right? The key step is really due to Cantor on this, right? Now there is one more step and I forgot, and I have to actually do little more model theory before I can prove this, and I forgot that I have not yet developed all this. This is called the wash-what test. Okay, so I'll come to that. So, but before that, this is an important thing that I want to. How do you show that? Forget all this stuff. We'll get to it later. Right now, let's just say that if I take any two countable models, right? Take two countable linear orders, right, without first and last elements, I claim that they are isomorphic. How do you prove that they are isomorphic? I have to build a bijection, right? Okay. Remember that these are countable. So let me enumerate x1 to be some a1, a2, and so on, and x2 is b1, b2, and so on, right? How do you build a bijection? So we'll get to this later. Let's not do it in a hurry. As I said, I want to do a little more model theory. That's a more complicated theorem. I realize that I need to build up a little more machinery before I get to showing that reals and rationals are not distinguishable. But let's just do this. So the statement is only proposition any two countable are isomorphic, right? So I want to build a bijection okay. So, and I want to illustrate something in the process, and that is more important for me right now, which is that you do it by what is called back and forth construction. This kind of back and forth construction works very nicely for countable structures, finite or enumerable countably infinite structures. And what is the idea? So you do it in stages. At stage 2n, you take element an and map it to some bj, right? Until this I have come so far, and now I have got an. This maps to this, this maps to this, this maps to this, and so on, and I pick some bj. At stage 2n plus 1, you take bn and map it to some ai, right? In such a way that the whatever you have got so far is isomorphic, and at each step you extend the isomorphism, right? You have a partial isomorphism at this stage so far. What is, we are now having only order, right? There is nothing else to interpret. There is no constant symbol functions, nothing. What we are saying is that it's the bijection that we are building is order preserving. That's all we are saying, right? Up till the stage, whatever you have mapped, if A1 is less than A2, B1 is less than B2 as well, right? H of A1 is less than H of A2. If similarly, if B1 is less than B2, H of B1 is less than H inverse is, it's a bijection, right? So I'll use the same, right? H inverse of B1 is less than H inverse of B2. This is what you want. So how do you do this? Well, so far you have mapped all this, right? So let's say that these are all the elements that are mapped. This is the A side and this is the B side. Now I get a new element an. What are the possibilities for this an? It can be below all the elements that I have already mapped, right? If it's somewhere here, I choose an appropriate element here and map. This is case 1. If it is here above all of them, I choose another element above all of them and map. Yeah? Is it clear what I am saying? If I have already mapped elements, let's see that. Look at this. Yeah? If I have already mapped elements like these, right? And now I get a new element which is here, which is above all of them on the A side. Choose B which is here, above all these. So let's call these A1, A2, A3, A4, B1, B2, B3, B4, right? So this is one case. If it is below all of them, you map it to an element below. This is the case 2. What if it's somewhere in between? If it's somewhere in between, it can only be, let's say, between A2 and A3. It should be between one of them. This is the case 3. But then the structure is dense, and therefore I can always find this is an here, and I can find a bn which is appropriate here, right? So because it has no minimal element, I can always pick something below. Because it has got no maximal element, if you give me something above, I can map with something above. If you give me something in between, being dense, I can always find an element that is. This is the idea. And this says that I can map any given A element to a B element. Now, since it's countable, I am alternating, right? Now I take, so this is an odd stage. Now I have to get a B5. For B5, I have to find an A5, right? How do I find an A5? Same thing. If it's above all of them, find an element above all of them. And there is an endless supply of new elements that is available, right? Equality also has to be preserved. The new element that I have got is not equal to any of them, so the mapped element also is not equal to any of them. But there is a big supply available, right? This is a countable order, this is an infinite model, there is always an element that is greater than all of them, so I can pick that. Similarly, if you give me something below, there are plenty of elements below, I can always pick one. If you give me something in between, again I pick something because it's dense. So simply using the fact that it's first a total order, everything has to be either below or above or in between, right, linear order, and dense, and without this I can. The details are straightforward, not, it's a matter of writing, but the more important thing is to learn this idea of back and forth construction. Back and forth, earlier, just a little while ago, Swapnil was asking about, but you have to prove that it's a isomorphism, right? When you set up an isomorphism, how do you do that, right? At least in the case of countable models, there is a. Now, you can set up something like that for arbitrary models also. For you index it by ordinals, and you say for successor ordinals, this is what I'll do. Then for limit ordinals, I'll take the limit elements and map to limit elements appropriately. So you can do, but that's more complicated. But at least for countable models, this is a very simple way of showing. And this says that any two countable globals are isomorphic, right? That's what it says. Cantor's theorem says something stronger. If you take any countable dense linear order without first and last elements, it's actually isomorphic to the rationals, the ordering of rationals. Now comes something interesting. Well, if any two of these models are isomorphic, okay, now comes the interesting theorem. There is a theorem, but that requires some machinery. Maybe I shouldn't get into that, we will get to it next time. So, we only talked about equivalence of models, and there are also, from all this now we can get many interesting theorems. Well, Monte theory full of many such theorems. We'll confine our attention to some small things. For instance, we can show that something that we saw already. Okay, let me mention that. Okay, I don't think we have time for a lot of things, but at least a few observations we can make. Yeah. Actually, there is also Tarski. First thing is, I don't like this. What did I do with that pen, which was writing well? Seem to have mixed it up somewhere. If a set of sentences has a model at all, right, then it has a countable model. Now, here I am assuming that L is countable. Why is this true? We've already proved it. How did we prove it? Well, completeness theorem, right? If it is satisfiable, it's consistent, right? It's consistent in your Hilbert system. Soundness means, see, completeness says that every consistent set is satisfiable. Soundness says that every satisfiable set is consistent, right? But then, for a consistent set, when we constructed a model, we showed that it's satisfiable, we set up a countable model, right? And therefore, as a consequence, we get that if your language is countable, any set of formulas that has a model at all has a countable model. And this is called the downward Löwenheim-Skolem theorem. Why is it called downward theorem? In general, it may have a model of arbitrary cardinality, right? So, in particular, if you were talking about the reals, for instance, right, and that's where we are getting to, right, reals with the ordering, right? It doesn't matter if you were writing a set of sentences, if it has a model at all, it has a countable model. Now, this is actually can be strengthened to something better. Let me just state it for the record. We are not going to do much with these things. Let me, or yeah, if in general, if L has cardinality lambda, now you can strengthen this to if gamma has a model, is a set of L formulas, then if you happen to have a language whose cardinality was lambda, not just countable, but arbitrary cardinality, that means you have to prove the completeness theorem for not, we did the completeness theorem for countable languages. Where did we use that the language is countable? Repeatedly when we did the Lindenbaum construction, right? Enumerate the formulas, right? Alpha 1 to alpha 2, examine them, add if it is consistent. If it's of the form there exists alpha, throw in, and then there we said it's countable, therefore there is something, there is a next new element available, put that in, blah blah. So we were using that fact. But actually when I was doing witnesses, I was careful because I use variables. Variables is always countable. What is the cardinality of the language? The set of constant symbols, function symbols, and so on. So in particular, constant symbols, right? So for instance, names, right? For instance, if you put in real numbers as names, right, your cardinality is uncountable, right? The cardinality of the continuum. Now, it so happens that you can reprove the Lindenbaum construction. You don't have to go through the way I did it, right? For those who care about such things, it doesn't matter what the cardinality of the language is. Whatever be the cardinality lambda that you start with, you can do a very similar construction. How will you do? Again, you index it by ordinals, and for successor ordinals, you proceed exactly like I did. You know, alpha plus 1, you look at alpha and add if it is consistent, etc. For limit ordinals, take the union of all those things that are less. But if you don't worry about it. This just says that this statement itself actually can be strengthened to this. Actually, it can be done the other way. That is the upward theorem, which says that if gamma has a model, then any cardinality greater than or equal to the cardinality of L. This is interesting. What does this say? If you have gamma, if you have, it has a model at all, if it has infinite models, yeah, this is important. If gamma has infinite models, yeah, if it has infinite models, so all this is only for gamma has infinite models. Because if it has only finite models, of course, there is nothing you can do to get countable models. What it says is that if the cardinality of, let's say it's a countable language, right? So you know it has a countable model. What it says is that I give you any arbitrary cardinality, I can always build a model of that size. How do I do that? Well, we already know a trick for doing that. What is that? Except that we didn't do it with uncountable sets and so on, right? Expand the language, right? So assume, you have some kappa many elements to add, right? Write that many inequalities, C1 not equal to C2, have lots of constant symbols of that kind, think of it as reals for instance, right? And put not equal to, take gamma and take the union of these and use compactness, right? How do you use compactness? Show that every finite subset is satisfiable. Well, gamma already has an infinite model, and I take any particular finite subset of the new elements, who cares what cardinality that is, right? So I'll get an infinite model, right? So since every finite subset is satisfiable, the whole set is satisfiable. It's some more tricky work to make sure that the cardinality is exactly the same, etc. But all this is to say that the size of mod, if your theory that you are looking at admits infinite models at all, right? You can blow up as you like, work with whatever cardinality you like. Okay. Yeah.
Sir, for downward Lowenheim's locking theorem,
Yeah.
is infinite model necessary?
Yes, it is necessary because, well, in general, when you say countable, you include finite as well. So you don't have to worry about for the downward case. You're right. If it has a model at all, if it has a finite model that includes, so in that sense, yes. But if I want it to be for arbitrary cardinality, right, then I need infinite models. For the second one, I certainly need it. So for uniformity's sake, it's better to keep. That's all. I agree. Because the formula may have only finite models, in which case you can't do much about that, right? You can't blow up the cardinality, right?
Yes.
So you can say there are exactly k elements in the model, right? Then you can't change the size of models, right? So this is important because when you compare models of different cardinality, right? When you want to show that they are elementally equivalent or something like that, it's important to keep all these things in mind, right? You may be able to blow up the size of models and so on as needed, but we'll see. Okay, we'll take up this. I'm not going to do too much of the arbitrary cardinality and so on. This is just to say that you can do. But what is very interesting is that even with reals and so on, I can talk about countable models, right? So there are countable models that you can take, right? And except that, what do they miss? And we can see. So more work to be done. I had hoped to do more, but going a bit slowly. Yeah. So my main point is to build enough techniques so we can talk about things being undefinable, right? And use elementary equivalence in the process. And then we'll see that when we specialize to finite models, things are, very similar constructions exist, but slightly different techniques are also needed. We'll get to that next time. Okay, thank you.
Sir, when will the previous videos be uploaded lectures?
Oh, I'll find out. It's some Diwali holiday. Yeah.
Okay.
Yeah. Anything else? Yeah. Anything else? Okay. Thank you.